Good evening for everybody in China. Hello to people from all over the world I see that are participating. It's an honor to be part of this webinar with all these wonderful sponsors and partners. And thank you for your time. Thank you all for being here. The presentation is going to be split up into a brief introduction, and then I'm going to describe the theory of constraints in general, followed by the theory of constraints applied to manufacturing, to production, and then the theory of constraints applied to project management, something called critical chain, and finally a brief conclusion. And I will explain the choice of those chapters in the next few minutes. As presumably was maybe mentioned in the introduction by my various Chinese partners, but since I don't speak Chinese, I'm not sure, so excuse me if I'm repeating things. For me, this event was started by some people I met in 2017 in Guangzhou, when there was a Theory of Constraints conference with over 1,000 people. And so I met a number of people, and we've been in contact ever since, and that has led to the partnership that we have created with SupplyWe. That partnership for me was fairly obvious and natural because we share two fundamental. Something's happening to my screen. It's not me. Two fundamental things, which is one, we're focused on producing results with our clients. I know all consultants say that, but I believe that Marris Consulting has a reputation for being absolutely obsessed by producing results, fast, spectacular, durable results, and I know that SupplyWe has the same obsession to produce results. And the second important thing is how are those results produced. And again, what we share is the idea that there is not one way of producing these results. There are a number of approaches and ideas in the world that are worth understanding. In particular, the most well-known one in the world today, Lean, from Toyota. But there is also the theory of constraints. There is Six Sigma or Lean Six Sigma. There is Industry 4.0. There is DDMRP. There is the list is long, right? And SupplyWe and ourselves, we always try and produce the right cocktail, the right mix of those things for a given company, for a given problem to be solved. And so that's what meant that this partnership that we have was obvious to me. Let me present myself briefly. I'm speaking to you from a grey, cold Paris, France, where I'm based. My journey started, in fact, in terms of improving the performance of companies in 1984, well over 30 years ago. I'll stop counting. When I discovered what we call Lean, or the Toyota way today, and a bit later I worked with someone called Eli Yahoo Goldratt, who is the founder of the Theory of Constraints. And so in many ways what I've been doing is helping companies for over 30 years with a combination especially of Lean and the Theory of Constraints, but also quite often other things. And so that's me. I've written also a very boring textbook in French about how to apply the Theory of Constraints to manufacturing, but that is only available in French. So the company is based in Paris. We've got some people come to see us not to meet me, but to see the view out of our office, because we have a very nice view. That's the Eiffel Tower there. We have one of the nicest offices in Paris. And we're a team of 12 consultants with lots of partners such as SupplyWe, and we do a lot of conferences, publish a lot of videos and all that sort of thing. Okay. we've had the honor and pleasure of working for all sorts of companies. I know this is being organized by the association which deals with SMEs in one of the provinces in China, and although there are many big names here on this slide, please understand that more than 2/3 of our business is done with small and medium enterprises. So I know companies of 10 people, 100 people, 10,000 people, or 100,000 people. Okay, so the names there are well-known names and big names, but we do a lot of work with SMEs, and we'll see that maybe in the questions and answer session. I know all about running a small business as well. Okay, and maybe as you can see from the names, we work in any business at all. We making cars, trains, aeroplanes, rockets, hamburgers, chips, paint, paper, whatever. So we have we're generous. We're not focused on any particular industry, and I hope that is also a strength, because we know many solutions and ideas from many different industries, and we can combine them depending on the client situation. Okay, so today I've chosen to speak about the theory of constraints, but the reason for that is that I assume that many of you already know something about lean manufacturing, the Toyota way, lean product and process development, because it is the most used in the world, and there are a lot of things, a lot of conferences, a lot of books, such as these books here, which I recommend, in Chinese. So I'm therefore going to concentrate on the theory of constraints, because it is less well known, and therefore I hope you will find it more interesting if I talk about this other thing called the theory of constraints. Okay, but let's be very clear. I've chosen the theory of constraints, but for us and for me, lean is very, very important, and nothing we do does not have a significant input from the ideas of the lean approach, the Toyota way, whether it's lean manufacturing, lean engineering, or many other things. Okay, so I'm going to concentrate on the theory of constraints, but let me say it one more time. Lean is also very, very important, and you will see it in the case studies that I will be presenting. There is always quite a lot of lean as well as other things in there. Okay, so let me start by briefly summarizing the theory of constraints. The theory of constraints was imagined, created by Eliyahu Goldratt, who you can see here, and it began to be known in the world around 1984, when Eli Goldratt published this book, The Goal. I don't know how, unfortunately, to say it in Chinese, but it therefore exists in Chinese, and indeed it exists in 32 different languages. It is just about to reach 8 million copies sold in the world. It is by far the best seller of all books on management of organizations, if you accept it as a book, because it is not a textbook, it is a novel, it is a story. It is the story of someone who saves his factory by discovering the ideas of the theory of constraints. Okay, and even though that book is old, published originally in 1984, before internet, for instance, it is still remarkably pertinent. And for those of you who are listening and who have not read it, well, please buy it and read it. Okay, for those of you who've read it more than 5 years ago, please read it again. Whatever your ideas about the theory of constraints, whatever I manage to convince you about the theory of constraints in the coming hour, that book is considered to be very important. It changes people's mindsets, and it's worth rereading very often, right? But it is a novel, and it doesn't tell you much about how to do it. Okay, so I hope I will help with the how to do things in the coming in this webinar. Okay. This is my one-page summary of the theory of constraints, which is not a very easy thing to do. Okay, and the idea is simple but fundamental. organizations try to distribute the work equitably, evenly in their organization, in all the different parts of their production and in all their different departments, from purchasing to human resources, to accounting, to production, to maintenance, right? Everywhere, when you do your budgets, right, you try to put just the right quantity of resources, whether it's people and or machines, in the various parts of your organization, so that everybody has just the right amount of work. That is the idea of a budget, right? And you do this so that you don't waste money by paying people who will not have work, and you want to avoid having a department where there are not enough people, right? If you did it wrong and there were not enough people in accounting to emit the bills, that would be a silly situation, right? So you try and make sure that everybody has just the right amount of work. That's the traditional way of managing organizations, and indeed it is still the reasonable way of doing things, although I will comment on that at the end of the presentation. But unfortunately it is no longer possible to do that very well, because we live in today's world, which, to use the term VUCA, V-U-C-A, it is volatile, things are changing all the time. It is complex, lots of interactions in the supply chains, in the economy, in the politics, in whatever, ambiguous, and so forth. It's hard to forecast exactly what we're going to be doing, right? We don't know what we're going to be selling in 6 months' time exactly. So the world is harder and harder to forecast, to know where we're going, and yet the inertia that we have to organize ourselves has not changed that much. It still takes about the same amount of time to hire somebody and train them for a job in the factory or in accounting. It still takes about the same amount of time to buy and install a machine, right? We're talking about weeks and months, and therefore it is now basically impossible to distribute the work equitably in an organization. And that is what the theory of constraints is all about. Somewhere in your system there is not enough capacity compared to the other resources, right? And that is the constraint of the system. That constraint will determine what your company can do, what your company can sell, right? And in this example, if you imagine the flow of work coming from the beginning here down to the end, and this is what you sell, okay? The different diameters of these pipes between the tanks represents the capacity that they have, and somewhere in the system you have a resource that has the less capacity than all the others, okay? So the theory of constraints is all about finding this constraint, and once you've found it, of course, you want to try and get it to produce as much as possible, try to get as much flowing through here as possible, because that is determining what you sell, nothing else, okay? And as a result, in fact, you end up with a dual system, a dual set of rules. You have different rules depending on whether you're talking about the constraint or whether you're talking about non-constraints, okay? And that is the theory of constraints. This kicker here, the sum of local optimums is not equal to the global optimum, is an important point, which becomes obvious when you see it like this, but people tend to forget. It means that, for instance, there is absolutely no point in asking this resource here to work as much as possible according to its capacity, which is there, because if they do that, they will just pour a lot of inventory, a lot of work into the system, which cannot be sold because it can't get past the constraint. Okay, so you should not aim to have full utilization of all your resources in your company. Only the constraint needs to be utilized all the time, activated all the time. The others have to learn to stop working. Okay, so that's the one-page summary. I believe that what I've just said is very important because it is getting more and more pertinent every year. That is to say, the visibility is decreasing and continuity that organizations have of balancing their company, balancing the capacities, is reducing year by year. So to my mind, the theory of constraints is already very important, but its importance is going to increase year by year in the future as visibility reduces further and further, and it is more and more difficult to have just the right number of machines and the right number of people in your different boxes in your organization. This is the fundamental way of working within the theory of constraints. It is got, it's usually called the 5 focusing steps, right? There are 5 steps here, or the process of ongoing improvement. And it's the way you implement the theory of constraints. The first thing you do, obviously, is to find your constraint, identify your constraint, okay? It's quite easy to do in a factory. It's slightly more difficult to do in a project environment, which is the 2 things I'm going to be talking about today. Once you've found it, of course, since you know that it determines how much you're going to sell, right? You want to exploit it. You want to use it as well as possible, as much as possible. You want to get every second, every drop out of that machine, right? So you exploit, and it's pointed out here because step 2 and step 4 are fairly similar, but step 2 is what I can do immediately, right now, without spending any money. This afternoon, what can I do to get more out of the constraint? Okay. Then there is something, the third step is subordinate, which is in fact to make sure that the non-constraints, the other resources, don't produce more than the constraint can manage. And again, going back to this diagram, its subordinate is to make sure that what this machine does, what happens here, is coordinated with what can go through here, so that you don't get what we have in this diagram, with lots of things piling up everywhere, big queues of work, right? So you want to subordinate everybody else to what is going on the constraint. And I pointed out that this is probably the most difficult step, because it's true that it breaks the traditional objective target that most people have, which is, I want to see my people and my machines working all the time, because you no longer want people to be working all the time on their different machines. The only machine that must continue working all the time is the constraint. The others have to learn to stop working, and that's why it's difficult. It's a big cultural change. Okay. Elevate, everybody loves. Nobody has a problem with that. You're allowed to spend money, buy a new machine, hire more people, and so forth. That's fairly easy. And 5, it's just that if you do this 1, 2, 3, 4, right, you're going to increase the capacity of the constraint more and more. And then as you increase it, the constraint is going to appear somewhere else, right? So once it's moved, it's gone to somewhere else, you find it again, and so you go back to step 1, where's the constraint now, and you start again. That's what the continuous process of ongoing improvement. Okay. This point here about choosing a constraint, I will discuss at the end of the presentation. So, this slide tries to summarize what the theory of constraints is. I'm afraid that, you know, just like Lean, every consultant has a different way of presenting these things. This is my way of presenting what the theory of constraints is. And we're going to concentrate today on just these 2 parts. This part about managing production, and this part about managing projects. But let me just mention that there are other aspects, other elements of the theory of constraints, which is dealing with supply chains, okay, there's another whole body of knowledge about what you do if you have a constraint in your marketing and or your sales, okay, and so I'm going to be concentrating here. The second line down here is more transverse global ideas. Throughput accounting is how to take decisions, financial decisions, based on the ideas of the theory of constraints. This I've put in grey because it's my personal opinion. I think that Eddie Goldrattz has said a lot of interesting things about data, big data, information, and so forth. So I regret that he's deceased. He died over 10 years ago. But I regret him not being able to comment on all the trends such as big data, because he wrote a lot of very interesting things about data and information. This part here is the thinking processes, or the logical thinking processes. Elie Goldratt was a physicist, and he loved logic, and he tried very hard throughout his life to get people to think more logically and decide more logically. So there's a big part of the theory of constraints which is all about trying to be more logical in one's analysis, one's problem solving, and what the definition of one's tactics and strategy. Okay, and finally, just here saying that, you know, I'm describing the theory of constraints in 2020, and no doubt it will evolve in the coming years, and other things will be added or changed as life changes. So let us start now with the theory of constraints in production. The way of managing flow in a factory using the theory of constraints is called the drum buffer rope. Okay, and it works in the following way. The first thing is that since we know now that it is this resource, this red one, which is the bottleneck, right, surrounded by non-bottlenecks, the blue ones, this is what is going to determine how much is produced in the factory. Okay, so it is going to beat the rhythm. It is going to be the drum of the system, and it will define what is done in the factory. Okay, so you look at your order book or what you want to produce, and you first thing you do is decide what I'm going to do with my constraint or bottleneck. Okay, and so you plan that, right? And the second point, the rope, is since I'm planning to do that on this resource, I need to launch the raw materials corresponding to that work in a synchronized fashion a bit before, so that the work will arrive in front of the bottleneck at the right time. So if, for instance, there is 3 days of work here to go through these 3 stages, right? 1 day to do that, 1 day to do that, and 1 day to do that. And if I'm planning to do something, some particular product on this machine in 6 days' time, then the rope says I will have to start 6 days minus 3. I should start in 3 days' time. Okay, but if we do that, there is a risk that if there are problems here, whatever they are, quality problems, absenteeism, any kind of problem, the product will arrive late for the bottleneck, and the bottleneck or the constraint will stop. So there is the final element, the third element of the solution, which is called the buffer, okay, which is defined in time. For instance, let's say 2 days, right, in this example, and it is inserted just in front of the bottleneck to make sure that it will be protected against problems, against variability, before it upstream from its production. So to go back to my example, if I'm planning to produce something in 6 days' time, and it takes 3 days to do the operations before, and I've decided to protect myself against 2 days of problems, I'm going to have 6 minus 3 minus 2 equals 5. I'm going to launch tomorrow, right? 6 minus 3 minus 2 is 1, so tomorrow I launch. And in that way, I will limit the amount of inventory I have in front of the bottleneck, but not too much. I will ensure that the bottleneck is protected against anything up to 2 days of problems, and that will probably make sure that the bottleneck never stops, while maintaining the level of inventory at a reasonable level in front of the bottleneck. Okay, so this buffer here protects the throughput, the sales of the company. There is a second bottleneck here. Its purpose is different. It is to protect due date performance, right? The quality of your service. If you promise something on such a date, to make sure that it will be finished in time, and to absorb any problems you might have in these 3 operations after the bottleneck, then you have another time buffer here, which is maybe a complicated way of saying I will plan to finish all my orders 2 days before I promise them, so I'm therefore protected against 2 days of problems. Okay, and if you do that properly set up, you will have a system with very high efficiency, since you will get the maximum of sales and you will finish everything on time. You will have 100% due date performance. That is the simple traditional way of managing a production facility when you have a bottleneck. Okay. Just to cover something, because I know that throughout the world, I'm not saying this is any better or worse in China than it is in France where I live, or elsewhere. Let me just remind you of one very important element about inventory and queue times and lead times. Okay, it is called Little's law by the person who formalized the logic. And it says that the work in progress or inventory that I have in my factory is directly proportional to my lead times. Okay, the more inventory I have in my system, the longer my lead times will be going through that system. So if I imagine things here as a simple tank where the raw materials come in here through a tap and what is sold goes out of here through a pipe. Okay. The more liquid I have in my tank, the longer it will take on average for a drop of water to go from the tap to here, right? So the more inventory I have in my system, the longer the lead times are going to be. Okay, we'll talk a lot about this, because whatever the approach, all the approaches trying to improve the performance of operations in the world, all based on improving flow. Whether it's just-in-time flow from lean manufacturing, or the drum buffer rope from theory of constraints, or anything, we're always trying to get things to flow through the system as quickly as possible. Right? So this is fundamental to understand that. And you will see that one of the things in many of the examples that we use is quite simple. It starts with the idea that you probably have today too much inventory in your company. Right? There's too much water, too many things inside your factories, in your workshops and so forth. And to reduce the quantity that you have, you implement the 2-for-1 rule, which is, since I want to reduce the quantity I have in my factory, I will only launch one thing when I've finished 2 things. That's the 2-for-1 rule. When I finish 2 objects, I can launch a new object. Therefore, little by little, I will reduce the inventory in my factory and get faster and faster, right? And that might sound crazy, but it's based on a lot of experience, which is that it is very, very rare to find companies that do not have enough inventory. They all have too much, or much too much, or much too much inventory in their system. Okay, so this is a simple rule to reduce the inventory, which you'll see that we use in about 80% of our projects, in fact. Enough theory for a moment. Let's go and take a look at a practical example. This, as you can see, is the Safran Group, which is a large aeronautic equipment manufacturer. And the example I'm giving you here is basically an SME, a small factory of 400 people, part of Safran, which has got 70,000 people, I think. And so this is the story of this one factory. They had a problem that they were not delivering on time, and this was getting very, very difficult because their clients, Airbus and others, had to stop their production facilities. They made flight control systems, what makes the plane go left or right or up and down. They had, because it was very important, already spent a lot of time and money buying machines, hiring more people and whatever to try and catch up and deliver on time, but it wasn't succeeding. Okay, and when we asked them what the problem was, they said, "Oh, we know what the problem is. We've got these bottlenecks, these 7 bottlenecks here. Okay, and that is why we're always late. But we're working on it, and our computer system says that we will soon have solved the problem, because if the red lines here that you can see are the capacity and the blue lines are the workload, the quantity of work they have to do, right? They said, you see, in 2 months' time, this machine will have caught up and it will be okay. And this machine will catch up in 1 month. In 1 month, it will catch the backlog okay, and so forth. And this one's going to take a bit more time and whatever. So they kept saying, we know we have bottlenecks, but soon it will get better. And the problem was that they'd been saying that every month for 3 years. Okay, so I was asked to have a look at what was going on. I went to the factory, and within an hour of just walking through this fairly small factory, okay, I realized that the bottleneck was not what they were saying at all. It was not any of those 7 expensive, nice looking machines. It was quality control. Okay, this is the inventory in the factory. There's inside each of these boxes there are parts being machined, right? This is aeronautics, so in just one of these trays there will be, I don't know, let's say 50,000 euro there in that box. What you're looking at here is about 10 million euros of inventory, because this is all very, very expensive aeronautical equipment, right? These little parts, big like this, but which cost 100 euros to make and that sort of stuff, right? So there was a huge queue of work waiting for quality control. Okay, out of the more than 1,000 work orders that they had in their factory, 35% of them were queued up in front of quality control. In fact, you can't see quality control. Quality control is behind the wall of inventory. It's hidden behind there. It's there, right? And if I put this example in here, by the way, it's on purpose. As we'll see as I go through the rest, very often in today's world, quality control is the capacity constraint of manufacturing organizations. In fact, it's also the constraint in some project organizations when developing new products. But anyway, in this case, it wasn't the expensive machines. That's what they hoped, but in fact, it was their quality control. Okay, so once we'd done that, step 1, identify the constraint, we better exploited it. Okay, and we basically launched 2 different actions: better exploit the constraint and reduce the work in process in the system. Okay, and just to get you listening a bit better, these are the results. Okay, that very quickly we reduced the inventory by 80%, and therefore we reduced the lead times by 80%. So you can see the quality control department here. That picture was taken just before we took the shells away, because we didn't want to have shells because it's bad for people's health. It means that people want to put things on them. And we increased the throughput, the quantity made by the factory, and the productivity by 30%. Okay, 80% reduction in lead times, 30% reduction in 30% improvement in productivity, and we just did that with 2 simple actions. Right? These 2 simple actions were to exploit the constraint, more management attention once they'd realized that was the problem and not the machines. They spent more time going to see them. Sometimes some silly small investments. Their photocopying machine had broken down several months before, and so they had to borrow the photocopying machine from the accounting department, which means they were wasting time when they had to make photocopies of their quality documents. So we got them a photocopying machine, and that helped, and so forth. And we did a lot of things. I won't go into the details here. Okay, and in the subordinate and reduce work in process, we applied the 2-for-1 rule. They were not allowed to launch a new batch into the factory before they had finished 2 batches. Okay, and we did other stuff. I won't have the time to describe it all. Okay, and that leads to this steep curve in reduction and in inventory. Okay, they had 50,000 different parts in the system when we started. They went down quickly to 12,000. Now they're even further down. They went a lot further than that. Okay, and yes, the story finished happily, because they were probably the worst factory out of 70 factories in the group when we started, but very quickly they became the best factory in the Safran group, and they won a prize from their main client Airbus, and lots of other good and nice things. Okay, let me just, having said that, please remind you or repeat that this was not just the theory of constraints, right? There was quite a lot of lean work done in that project that I just showed you. Okay, I'm talking about theory constraints, so I described the theory constraints things. But we did SMEDs, reduction in machine changeovers. We did a lot of work to improve the quality. We did a lot of lean things in there too. Okay, so let me just repeat once again what I tried to say in the introduction. For me, you can, indeed you should, combine the theory of constraints with lean. They're both trying to do the same thing, trying to get things to flow faster, trying to get the best possible performance out of the system. And frankly, there's very little disagreement between them. It's mostly consultants that claim that there's a conflict between the theory of constraints and lean. Most practitioners are quite happy mixing in a bit of lean and a bit of theory of constraints and a bit of Deming and a bit of something else, whatever. Okay, and that's what we do also. Okay, so I'm talking about the theory of constraints, but please let me emphasize that we were also using quite a lot of lean in that example and in our work in general. Okay, maybe there'll be some questions, and we can come back to this in the questions and answer session, but it is clearly one of the things that we believe in very strongly, both SupplyWe and Marris Consulting. Another little example, this one in the automotive industry, and I'm just running slow. This is probably one of the most high performance factories in the world that I have ever met anyway. It was already very, very, very good when we started. 1,000 people in the middle of Mexican desert producing alternators for cars. Okay, and the demand for their products had gone up very fast and very sharply, and they were getting behind in production, and therefore their clients, General Motors and the whole of the American continent, in fact, were starting to scream and shout, so they had to increase the output of their factory as quickly as possible, and they were already buying lots of machines and hiring lots of people. Right? Let's take the example. There were 20 autonomous production units. This is one of them. Okay, so the alternator rotor is produced here, and it goes around here through different machines. Okay. What did we do? Well, we had to find the bottleneck. It was this particular machine, right? This machine was slightly slower than all the others. Okay, so we therefore had to apply the theory of constraints. Now we've done step one, identify. Step two, better exploit it. And in this case, it was a question of slightly increasing the inventory in front of the machine, because all this was on conveyor belts. Okay, and this machine was sometimes stopping the bottleneck. So we increased a little bit the amount of inventory here. In this particular case, when we started, we increased it by adding about 3 minutes of buffer only. 3 minutes of buffer. And that immediately increased the performance of this by 17% within an hour. And since that was the bottleneck of the factory, the whole factory of 1,000 people immediately starting producing 17% more parts per day, right? That was the bottleneck. That's the power of the theory of constraints. We did, again, lots of other things. I just want to emphasize once again, we don't just do theory of constraints. There are many other ideas that are implemented, and so we did a lot of lean actions, Poker-Yokes, SMEDs, 5S, and other things that were involved in getting those results. Okay. Yet another example, which I won't try to detail. This is the world leader and inventor of the ball bearing, and same sort of results: significant decreases in lead time, increases in productivity. This one is interesting because they had a very silly, regrettable, cheap bottleneck. Maybe we'll come back to that one in questions and answers. Again, this one more to provoke eventual questions at the end of my presentation, because this is something completely different. This is the world leader in fast food, McDonald's, not to name it, and we applied the same ideas, and that managed to reduce the wait times of the clients in the fast food restaurants by 60%. It basically got rid of all the losses of material, excess production, and the customer complaints were divided by 7, etc., etc., etc. Okay, so I can't describe all these cases in such a short time. Just to say that these ideas can be applied to a factory, but they can be applied to a services factory, such as a fast food restaurant. Okay. So that's a very brief. Forgive me. It's difficult to give all the details. I wish I could in such a short time. That's my summary of what happens if you apply the theory constraints to factories, to production or repetitive production. And we're now going to talk about the other component, applying the theory constraints to projects. Okay. Again, the results are unbelievable for those of you who are discovering theory constraints here today. No doubt you think I'm just lying, because the sorts of results that you've seen, and it's getting worse as we go through the presentation, do sound impossible. Critical chain, and this is the data coming out of one of the books published recently based on 60 different examples, says that you can basically do your projects at least 40% faster, and you can increase the number of projects you finished a year by about 50%. Okay, well, that's in that book. In Marris Consulting, we expect in all our implementations to reduce the duration of projects by at least 50%, and to double the number of projects we do every year, and of course to finish them all on time. So how's that done? Well, a lot of people are doing it. That's not an exhaustive list. That's just an idea. All the different companies in the world already using critical chain, and we're adding to that list every month as we go. We do a lot of this. Okay. Finally, another good reason maybe for you to get interested is that, for example, last year, 2019, beg your pardon, in 2019, the best project of the year awarded by the Project Management Institute, which is the largest association managing project management professionals in the world with over 1 million members, awarded Embraer the best project of the year for the development of an aeroplane, the E190-E2 jet. Okay, because they used critical chain and finished 22 months early, right? Everybody else, when they develop airplanes, finishes late, very, very, very late, or very, very late. Embraer developed a new airplane and finished 22 months early. Yeah, okay, using critical chains. Anyway, how does it work? Like many of the ideas of the theory of constraints, it is extraordinarily simple. It's the beauty of the theory of constraints, really, if you understand it correctly, is that every single solution is very, very simple. And so here it is in basically 2 slides. When you plan a project, you break it down into a certain number of tasks, and you try and estimate how long those different tasks are going to take. Okay, and if we take this very simple example, this is a school book example, I'm sorry, with only a dozen tasks, of course. Okay, the project starts here and finishes here. Okay, so that's the important date. When will my project be finished? In the real world, right, you can have 100 tasks, 1,000 tasks, or for a submarine you can have, or an aircraft carrier, you'll have 50,000 tasks. Anyway, let's take this simple example. You have to estimate the duration of each task. So you go to the different people who are going to do these different tasks, and you ask them, how long is it going to take you to do your part of the project? Okay, and you want them to commit to a particular duration. Okay, so they do that. They say, this is going to take me 4 weeks, this is going to take me 3 weeks, this is going to take me 11 weeks, and so forth, right? And then you put it all together and you have a Gantt chart and so forth. That's the way you do it. The problem is you've killed the project already, because you've asked people to give one number, one estimate of the duration, and therefore and yet it is an uncertain world. This is a project environment. It's the first time they've actually done this, exactly this. Okay, so there's a lot of uncertainty in the duration, and you've asked for one number. You did not allow them to say, if I'm lucky it will take 4 weeks, but if I have problems it's going to take 10 weeks, which would have been a sensible answer. No, you asked for one number, and you're going to judge that person on whether they meet that commitment. Right? He said 11 weeks. I will not be happy if he takes more than 11 weeks. And the only way, therefore, that that person can survive is that they add local safety to their estimate of the duration, right? And this is what is represented here. The dark blue is what they think the work is going to take, if all goes well, on average. And this light blue thing here is the local safety, the local buffer that they gave themselves to protect themselves against problems, okay, so that they can honor their commitment to their boss here to have finished in 11 weeks. Okay, so we've created a system where everybody has safety, every single task has safety, right? And yet the project is going to finish late. Strange, isn't it? Right? I mean, if there's so much safety in the project, well, surely we're going to finish on time, you think. But as you know already, projects very rarely finish on time, right? And that is because, but I won't have time to describe it today, all the safety is wasted, right? All the safety is wasted in the system, and only the problems accumulate. So you put safety everywhere, but it's all wasted. That's why in the end the project will finish late. Okay, but unfortunately I won't have time to describe that in full detail today. So if we put that idea and apply it to projects, okay, let's imagine that we have we're developing a new product, right? A new electric car, right? Let's keep it very simple. Let's say there are 3 stages. There is a proof of concept, where I prove that my idea of an electric car is going to work. Then there is a period where I do the prototype. It's going to take me 16 months. And a period where I do the industrial ramp up and I get to the first pre-series, right? I'm developing a new product, and so it's going to take me 4 plus 16 plus 12. It's going to take me 32 months to develop. Okay, and how did I get those numbers? I went to see this person and I said, you know, for this new car, how long is it going to take you to prove it's okay? And he said 4 months, just looking out the window. He went to see the person in charge of prototypes. I think it's going to take me 16 months. And the last person, 12 months. And in fact, the car is going to be launched late, right? Like everything gets so often gets finished late. Okay, and that was because we asked people for commitments. Okay, so now we just do it completely differently with the same car, right? The same electric car. We go and see this person and we say, tell me, for this new car, how long will it take you on average, if you only had that to do, to prove the concept? On average, you're allowed to be late. Okay, and they would give you a significantly shorter time because it's no longer a commitment to finish, right? And you do that throughout the system, and you break it down into 2 different times, and you're only interested in this focus duration. The focus duration is if all goes well, on average, and if I only have that to do in perfect working conditions, you know, how long would it take you? And so you keep all these focused durations, and you plan the project in that way, right? But since you know there will be problems, that's impossible, right? You add a buffer to absorb problems and uncertainty, and that buffer is big. It is about 1/3 of the duration of the project, right? Here we have 16 months of optimal, naive, optimistic execution, right? 2 plus 8 plus 6, and we have 8 months of buffer to absorb problems, right? That is how you plan in critical chain, and then you execute, and you execute it using this emblematic fever chart, which is here. Here is the project itself from the beginning to the end, right? I start here and I finish here, and on the vertical axis I have the buffer, right? I have this part here. I have the 8 months. So 16 months there, 8 months there. And I regularly see how it's going. And yes, I consume the buffer. That's perfectly normal. It is what it is there for. Okay? And as long as I stay in the green, I know everything's going very well. And if I'm up in the red, I know I have a problem. Right? And those colors, in fact, completely empirical, right? They're not calculated mathematically. They're just a simple idea that if you're down here, you have just normal problems and normal variability. And if you are up here, you have more problems and variability than you expected, and you could be late. Okay? And that is critical chain project management, which is why if you go back to that, which is developing an airplane, that's what happened to them, right? Now you can understand why I was pointing here. That was 22 months early finish. They finished it there because on the graph here, what the date you promise is here, right? The date you promise to the outside, to your salespeople for this new car is there, which is up here. So this finished early. I won't have time to go into all the details, but for those of you who know well the traditional project management approach, there's something called the critical path, which is here, and critical chain is the close cousin to the critical path, but it makes sure that you take into account conflicts of workload. In this example, Pierre is being asked to work on 2 things at the same time. Okay. And in critical chain, you take into account the available capacities. Okay, let me just see that there. Right, Pierre will first do one thing and then do the other. Let me get back to this. So again, please forgive me if in such a short time I can't describe all the elements of the critical chain. Let me just summarize the main points here. The first thing I've described already is that you ask people to re-estimate their times using focused durations, right? How long will it take you in perfect conditions, only working on that, without multitasking, without any problems, on average? It's an unrealistically optimistic or aggressive duration. It doesn't matter if they're late. Okay. We do resource leveling, that's to say we make sure that we don't overload the system and ask people to do several things at once. Okay, it might sound obvious to those that don't know the project world or the project environment, but it is rarely done. People rarely manage the capacity of project teams, in fact, not properly. You identify the critical chain. I'm going to show you in a second how do we do that. You start as late as possible. You start as late as possible. If you want to finish your projects on time, you must start them as late as possible. Maybe somebody will ask me some questions about that idea. And you insert buffers. Buffers, 2 types of buffers. I'll show you that in a second. Okay, so this is again a very simple example with a number of tasks finishing off. I've talked about this. This is the focus duration, right, where you re-estimate the times. So you get times that are much shorter. Let me just say one thing about that little trick. Some people say that what you do is you divide the durations by 2, right? Tack, tack, and then the project will go faster. Basically, they're right, but they're wrong. That's to say, you can reduce durations very significantly when you go to focus durations, but you do not do a top-down divide by 2 rule, because that will not work. What you do is you explain to everybody that has to guess a time what you're looking for, this definition here of a focus duration, and they will give you times that are much shorter. Right. The critical chain itself, that's the definition. Okay, but let's be clear that critical chain is an approach which has many things, such as buffers and fever charts. The technical definition of the critical chain is this one, close cousin to the critical path, but it takes into account resource dependencies, right? It doesn't force people to do 2 things at once. Okay, and There are in fact two types of buffers. I've talked a lot about this one here, the project buffer, right, which was what I've been talking about up until now. In fact, you also insert feeding buffers that are just as important. The idea being that the critical chain is the constraint of your project. It is what is going to determine the success or failure of the project. Right? It is the constraint of the project. And if we want that not to be impacted by the non-constraints that are here in blue, we need to make sure that the blue ones don't become late. And so we protect the critical chain, we protect the constraint from problems on the non-constraints. And once again, you see what these famous buffers of the theory of constraints turning up. Because then you know, if you do this properly, that the critical chain will always be there. It will not move around if there are problems, because they're protected against problems here. Okay? And you'll have a very stable critical chain, which people say is impossible, but look at all the companies using this technique and doing that, right? If you make sure the non-critical stuff stays non-critical, and then you can concentrate on the critical. And if you can do that, you have another beautiful thing, which is that the success or failure of the project will depend on how quickly and how well you do that sequence in red, which is the critical chain. And in many environments where it's pertinent, what we propose is that they have a mascot. If you've got a good sense of humor, you can, for instance, choose a big pig like this one here, right? And it's a big pink pig that went from one office to another. And so when everybody saw this big pink pig, they knew they had to let that person work. He was the critical part, and don't disturb him, let him work, because that person will determine the success or failure of the project, not the other people. Okay, so to play the relay race all the way down these tasks, we try and use a physical object, a big remarkable physical object, so that everybody knows what's going on. That's the fever chart once again. Just to remind you, you aim to finish around here, that's to say a little early, all your projects, which by the way is the way I presume all of you catch your airplanes, right? Do you miss your airplanes often? Probably not. And how do you avoid missing your airplanes? You wait in front of the boarding gate for 20 minutes or 1 hour, depending on how well you know the airport, right? The only way to finish all your uncertain projects on time is to finish them a little early. That's how you do it in the critical chain. And one of our clients in product development has a 98% finish on time with its clients that are Boeing, Airbus and so forth, right? In the real world, with clients that change their mind all the time, they finish all their new developments 98% on time. Okay, the three colors there are perfectly empirical. They're just guessed. Red is danger, green is okay, yellow you're going between the two. Okay. Now, that's an individual project. What happens with a portfolio? Well, the portfolio, in fact, is easy. Managing a project portfolio is easy. Now, those of you again who know the project management world will think I am crazy, because normally the worst job in the world is to be in charge of a portfolio of projects, because everybody is screaming at everybody, all the projects are late, it's not a good place, it's not a good job, right? But that is because all the projects were badly designed, badly planned and badly executed, so they're all going to be late, and so you spend your time in a lose-lose argument all the time. Imagine a world where each individual project was planned as I described and has a good probability of finishing early. Then in fact, if you're managing a collection, a portfolio of healthy projects, it's much easier than managing one project, because I can move people around from one project to another. I can reallocate. All I need is a system to redistribute the work between projects. So you put all your projects on one sheet of paper like this. You have the same fever chart as a portfolio, and you know you have a problem here. That is the most sick, that is the most worrying project in my portfolio. What can I do? And please note, you see it early, because probably you are all screaming and shouting about what's going on up here, right? That's to say, projects that are late and which one should I finish first. and you're looking at the next 2-3 weeks, 2-3 months. This one here has only just started, right? And it's now you can solve the problem, right? Maybe you don't agree with the client, or the marketing doesn't agree with your research and development, or whatever. There's something strange going on here, right? And 80% of them in the green. This is a real client's fever chart. This is the real world, right? 80% of your projects will finish early without even any managerial interference. And so when you need to help a project like this one, you say, okay, it so happens that the team doing project 20 can help project 1, so they just stop for 2 months doing their project and they help P1 solve their problem. Okay, that is the beauty and simplicity of portfolio management the critical chain way. You have a KPI, an indicator that is the size of a postcard, and it tells you everything you need to know to take all the decisions, and you can have very short and powerful meetings because you only have to take care of 1 or 2 projects that really need help. Okay. To be able to do that, there is one necessary condition which is important and difficult in the real world, which is you've got to make sure that you do not put more projects into your system than you have people or capacities, right? You want to avoid the flooding here, and it is even more important not to flood a project world than it is not to flood a production world, because in a project world, if you give them too many projects simultaneously, they will start multitasking, and multitasking kills. I will show you an example. Okay, so there's another part here which is all about making sure that you don't put into the system more projects than can be dealt with by the constraint. This is the fear constraint, so you need to find what department, what people in your organization are the capacity constraint, and you don't launch more projects into the system than what they can do. You see the similarity between managing projects and managing production there. Okay. This applies to projects in general, whatever they are, and the world of projects is huge, of course, right? It's developing products, we do a lot of that. It's engineering to order, we do a lot of that. Maintenance of airplanes, a lot of that. Developing software, etc., etc., etc. Right? These ideas are generic, right? Let me give you an example. This is a very, well, it's one of the largest companies in the world in the engineering field. But again, we're just going to talk about one of their factories, one of their SMEs. It was an independent company, 500 people, but part of a 300,000 person organization, multinational. They made these little gearboxes, right? You can see there's a person here, right? Cost between 50,000 and 500,000 euro. For instance, a gearbox that goes between a gas turbine and an electric generator in a power plant. You know, so these things have to spin around at 20,000 RPM for 25 years without failing, and they're kind of delicate things. Okay, so they were doing these. The company was 500 people. Every single object was different, right? There were it was non-repetitive engineering and non-repetitive manufacturing, because there are no 2 identical power plants. It all depends on a lot of things I can't describe, but you know, if they did 2 machines that were identical, that was once a year celebration. Otherwise, they were all different. Okay, they had 90 projects going on in this design office of 15 people. It took them 50 weeks, 50 weeks, to do all the work. That's to say, both designing it, but also producing the quality documentation, the instruction manual and all that stuff, right? And they were producing 1.8 projects per week. Okay, that's the starting point. Well, what did we do? We had a quick look in the office. It was this 15-person open space. Was everybody screaming, everybody on the phone, on whatever, running around. It was just a normal office, right? Just a normal office, with a lot of noise and a lot of interruptions and so forth, right? And that we changed. They were multitasking. To prove it, we actually measured how many tasks somebody did a day, and they were doing 60 different things per day. They were switching tasks every 7 minutes, right? So when they were trying to work out the tolerance here in microns to get this thing to float on oil and whatever, quite complicated machines, right? They did it for 7 minutes, and then they switched to another machine or another subject. They were going mad. Okay, and so we had to stop the multitasking because that kills, and we did. This is what happened. We implemented a rule called stop starting, start finishing. There is too much work in your office. There are 50 projects going on. That is madness, right? 50 projects for 15 people. That is impossible. You can't work properly. We need to reduce that quantity. Okay, so we will not launch any new designs into your office until we get back down to a reasonable level. And we went from 90 to 30 very quickly. And we did that by just stopping launching the new designs in, and asked them to concentrate on finishing. Right? Before, they were doing 1.8 a week. We implemented the new rule here, and a bit later they were doing 4.2 projects a week. Right? 130%, not 30, 130. Right? I went from 1.8 to 4.2 a week. Same people, same 15 people, designing the same things, just not a madhouse. Right? And in the transition, they actually went to 8 a week. They were doing 1.8, they went to 8 a week. Why? Because they started working on the things that were nearly finished, right? And so they purged the system out, quickly got back down to 30, and then stabilized at a performance where they had 4.2 a week, 130% increase in productivity, 130% increase in throughput. And by the way, since this was the bottleneck of the company, that's 500 people now producing 130% more, right? The whole company, the sales of the company went up 130%. It was the bottleneck, right? And they got a lot faster. It used to take them 50 weeks, right? It now took them 8 weeks to do a design. That is the crazy beauty of the theory of constraints applied to projects and critical chain. As I said, we do a lot in MRO, maintenance, repair, overhaul of big expensive objects such as aeroplanes and other things. This is an example with Embraer. There are lots of videos about this case. It's quite simple. We just divided the times by 2. But we also increased the productivity by 70%, 70. The labor mechanics productivity went up by 70% here. Okay, so the previous one 130, this one 70. You can ask some questions about this if you want at the questions and answer session. And to finish off about critical chain, just to say that probably the longest user, the company that's been using critical chain for the longest is Mazda Motor Company. They started using it in basically 2003, and they got to full usage about 12 years later, yeah, in 2014. It's now used all over the world, all over Mazda to design cars or parts of cars, and they swear by it, and they say in fact it saved their company. And by the way, in the real world, that can be a fever chart. This one was a fairly hectic story, obviously, and things were going all over the place. So please forgive me if I gave you a very simplistic, sometimes, presentation of the concepts, but it's hard to go through all this material in such a short time. To conclude, well, I assume one of the many questions will turn up will be, how do I find my bottleneck? It's true that if it's your first time, it's not that easy, and so I've just pointed out a few tricks. Please do not believe any calculations you may do. Don't believe your data in whatever the environment. The data is wrong. Go down to where it's happening, to the shop floor or to the offices in project management, and look for the biggest queues of work. Look for the biggest queues of work, right? Naturally, by the law of physics, the constraints are going to create the longest queue. So look for the longest queues and find it, okay? And watch out if your bottleneck is too good to be true. If somebody says, look, this is my big, beautiful machine and this is the bottleneck, in fact, their confusion is that is where the bottleneck should be, but it is not necessarily where the bottleneck is, right? So maybe your most expensive machine should be the bottleneck, but it probably isn't today. In our experience, it's very rare, unless you've been doing theory of constraints for a couple of years, and then you've got that. Okay, and don't worry if you hesitate. Just try it. Right? If this is the bottleneck, what would happen? Another little point here is that, in my mind, the ideas that I've been expressing should be applied in two different time horizons. One of them is the short term, how much money I'm going to make with my order book in the next week, in the next month, and in there is a constraint somewhere, probably somewhere in your operations, maybe a machine, but there is a constraint determining your future in the long term. How big is the company going to be in 3 years' time, right? How much growth is it going to have? And the constraint that determines the answer to that question is probably somewhere else. It could well be, for instance, in new product development, right? So you can perfectly well have a constraint that determines the performance in the short term somewhere in your factory, and simultaneously have a constraint that determines how much money you will make in the future, how much growth you can have, and that might well be in your engineering department. Okay. And finally, this is the last slide. Ultimately, for me, these ideas that I've been presenting go above and beyond the 5 focusing steps that I presented, where you just go around iteratively looking for the next bottleneck, right? You go capacity constraint hunting, bottleneck hunting, around and around. As I said, I think once you've been using these ideas for a few years, you will want to try and choose your bottleneck, choose your constraint. And just to give you my recommendation, I believe that the best bottleneck or the best constraint in a system is the thing that will cost the most time or money to turn into a non-constraint, which is a kind of complicated way maybe, but of saying, expensive things should be the constraint. Thank you very much. We'll be putting out a lot of new content and stuff, we and myself, videos, articles and so forth, so stay tuned. This is the beginning of a long series of stuff. And that's it from me. Thank you very much. Thank you for your time.